of this related rates problem with the lighthouse and the beam of light, and we had gotten it down to this point where we had dx dt, which was the rate at which the light beam was traveling up the shore, in terms of the secant squared of theta and the d theta dt. And the problem we had, better late than never, boys. Kids these days. There was a snowstorm outside yesterday.
Yeah, it delayed me.
Uh-huh. You had to like pep talk yourself to go outside after looking out and seeing the winter wonderland. Yeah. Okay. To be fair, it's not like this sort of thing happens every day in April, but yeah. Okay, so where was I before I was so rudely interrupted? We had it down to a formula for dx dt in terms of secant squared of theta and d theta dt. And the problem was we didn't know what secant squared of theta was. We know d theta dt because it was given as, what did we have, 4 pi radians per minute. That was the rate at which the lighthouse was rotating, twice per second. And then the secant squared part, well, we needed to look at this little triangle here. So at the point in time we were interested in was the moment that the beam of light actually was hitting the hotel, right? So it sweeps up the coast, and it's going to, at one instant in time, be pointing directly at the hotel. And we wanted to know how fast is it moving along the coast at that moment. Yeah? Okay, so the particular configuration we're interested in is when we have this sort of triangle where it's 100 on the base, and that was because the lighthouse was 100 yards or whatever offshore, and then 173 was the distance to the between the perpendicular and the hotel. Okay, so we got the, remember this, what we had set up? Yeah? Okay, so in that triangle, we need to compute what is secant squared of theta. Well, what is secant of theta in general? Right, what is secant defined as? 1 over cosine. Okay, so if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent, right? We don't know the hypotenuse in this triangle, but we can figure it out because of, pray tell, well, Pythagoras' theorem, right? So if we've got 100 and 173, then the hypotenuse would be this, right? Okay, and then we just need to number crunch because I don't know what that is. So let's just do square root of 100 squared plus 173 squared. And it's basically just shy of 200. Okay, and we should have known that in advance because 173 is basically like 100 times the square root of 3, just rounded a little bit. Okay, so it shouldn't be a shock that we got 200 because we basically have a 1, 2, square root of 3 right triangle. Okay, but anyway, what did we get, like 199.82, right? All right, is that okay? Yeah? Or exactly, what is it? It's the square root of 39,929, right? But basically just shy of 200. Okay, so now that we know that, what do we actually want? The secant, right? So what is the secant again? What's secant in general? 1 over cosine, or another way to say it is hypotenuse over adjacent. right? Because cosine's adjacent over hypotenuse. All right, so what's the hypotenuse? What did we get? This 199.82 squared would be 39,929. What's the adjacent side in the triangle? And sorry, my arithmetic's covering it up. The adjacent side was 100. So I have to square it, right, because it's secant squared. Yeah? Okay. And then what was dx dt? 4 pi. Okay, so one of the factors of 100 cancels, right? And so we have basically 399.29 times 4 pi, sorry. All right, and so let's just get a quick 399, what was it? 399.29 times 4 times, let's say 3.14159. So we're looking at what? 5,017.62. What were our units in this problem? I don't remember. What was the distance unit? Yards. And what was the time unit? Second or minute? Minute. Okay, so 5,000 yards per minute. Okay, now that's not a very useful unit, right? How fast is a yards per minute? Kind of slow, right? A yard per minute is kind of slow. 5,000 of them surely isn't, right? So let's convert this to feet per second, which is maybe a unit that would make more sense to us, right? So how am I going to do that? 360 no scope. Yeah, okay. Namely, we can set up a proportion, okay? And there's a lot of ways we could set up this proportion, but let's do, say, for example, 15 over 6 equals x plus y over x, okay? So if the two triangles are similar, then the corresponding parts are proportional, and this equation is one way to write that proportion. It's not the only way, but that'll work. We could have also done 6 is to x as 15 is to x plus y, but same difference. Okay. Good? Okay, so what would be maybe a good move at this point? Yeah, that sounds like a great move to me. Let's cross multiply and simplify things a little bit. Okay, so what do we get? 15x equals 6x plus 6y. And if I pop the 6x over, then I've got 9x equals 6y. Okay, good? All right, so what are we trying to find here? We're trying to find dx dt, right? The rate at which the length of the shadow is changing. Okay, so if I've got 9x equals 6y and I take the derivative of both sides, then what do I have? 9 dx dt equals 6 dy dt. Right? Okay, so now what? Yeah, we know what dy dt is, so dx dt would be 6 over 9 times dy dt. What was dy dt? 2. Okay, so it's 4/3 feet per second. Does that surprise you guys? Does that seem like a reasonable figure? You thought it would be more. Why? Okay. Also, are you surprised that that's actually slower than the rate at which he's walking? Okay. All right, but we're not finished, and perhaps the second part of the question will, illuminate, if you'll pardon the terribly chosen pun, what's going on, right? So what was the other question we were asked? The speed of the tip of the shadow. Okay. What is the speed of the tip of the shadow? Well, the tip of the shadow is how far away from the lamppost? batteries in it the other day. And now they're dead again. I'm not joking. Okay, anyway, work out these other two, and then I'm going to quit the stream here, and we'll just talk amongst ourselves. So, all right.